In this video, we're going to take a look at how to classify chemical reactions. We'll be using a system where we have 5 basic classifications and then one other one that basically, if it doesn't fit one of those 5, it'll be called an other reaction type. Once we've looked at how to classify the equations, then we'll take a look at some examples of balancing equations, classifying them, as well as predicting reactants in products. So the different types of reactions. So you remember that chemical changes involve new substances being created. We know from our earlier science classes that evidences for chemical change, if you were performing it in the lab, you might see a color change, you might see the production of a gas, bubbling or fizzing, you might see a temperature change. If the reaction starts to feel hot, the test tube or container starts to feel hot, it's producing heat. It's called an exothermic reaction. If it starts to feel cold, it's because it's absorbing heat, and that's an endothermic reaction. So temperature changes are one evidence of chemical change. Sometimes they produce odors. You can detect a noticeable new smell as a result of the chemical reaction. And often there's a precipitate that forms. You might be mixing solutions where everything's dissolved and suddenly something solid is appearing inside the solution. That solid substance appearing inside a solution is referred to as a precipitate, and that's a precipitation reaction. All right, so those are different properties of chemical reactions. In grade 11 chemistry, we look at chemical reactions and we classify them according to a system where we have 5 basic categories. The first reaction type, the simplest one, is called a synthesis reaction. Synthesis means creation, or to make something, you're synthesizing it. So in a synthesis reaction, the way to recognize it is to see that there are multiple reactants. Remember that everything on the left-hand side of the arrow, those are called reactants. And everything on the right-hand side of the arrow are products in the reaction. So when you have more than one reactant and only one product, notice I'm ignoring this number 2 out here. There's only one formula here, sodium chloride. So if you have multiple reactants but only one product, then you're taking 2 or more reactants and synthesizing a compound over here, this sodium chloride. Okay? So 2 or more reactants and only one product, that would be a synthesis reaction. Sometimes they're called composition reactions. And if the reactants are all elements, like we see here, then sometimes they're referred to as simple composition reactions. So when you have only elements combining to make a compound, that's a simple composition reaction. Or you can simply call it a synthesis reaction. A decomposition reaction can be thought of as the opposite of synthesis. So you have only one reactant, and it breaks apart into more than one product. Okay, so you'll see one substance on the left-hand side of the reaction and more than one substance on the right-hand side. You'll have a compound on the left and simpler things on the right. That's a decomposition reaction. If the decomposition reaction produces only elements, like we see here, so this compound water is breaking down into its elements, then we can add the word simple, just like earlier, and call this a simple decomposition reaction. Okay, so synthesis and decomposition are kind of the opposites of each other. In synthesis, you're taking multiple things and creating a single new thing. In decomposition, it's the opposite. You're taking a single substance and breaking it down into multiple substances. Single and double replacement reactions. These reactions, I like to use a dancing analogy. Okay, think of people dancing here. Let's take a look at, sorry, I've just highlighted the wrong 2 things. Single and double replacement are dancing reactions. In this first example, single replacement, you have a compound that's made up of ions, so silver nitrate. Think of that as two people dancing. We remember from our nomenclature unit that the silver is a cation positive and the nitrate is an anion negative, and they're attracted to each other. They're dancing together. Copper over here is just an element. Right now he's neutral, and he's going to go in there and ask one of these two people to dance with him. Okay, so you have a couple dancing. Copper's going to go in and ask one of them to dance with him. Right now, somebody's watching two people dance, and he's going to go ask them to dance. Right now, the copper has no charge. We can tell that there's no charge written beside it. But we know from our nomenclature unit that it typically becomes a charge of +2. It can actually have +1 or 2, but +2 is its most common charge. Right now, it has no charge, but it will become +2. If you know that it becomes +2, then it makes sense that it's going to be attracted to the negative ion over here, and so what you'll get is copper nitrate. Okay? You'll get copper 2 nitrate. And then the silver has lost its dancing partner, and you have silver by itself. So there's the single replacement reaction. You have a compound made of two ions, positive, negative, reacting with an element. Compound, element. And what happens is the element goes in, kicks out one of the ions, and you get a new compound and then a new element. Okay, there's the distinctive way to recognize single replacement. Okay, over here the copper is positive 2 technically, and the nitrates are negative, and now the silver over there is neutral, right? In a double replacement reaction, again, it's like a dancing analogy. You have two couples this time. So instead of an element with a compound, we have two ionic compounds. So we have a sodium dancing with a chloride, we have a silver dancing with a nitrate. And what's going to happen in this dancing analogy is that they trade partners. So you have two ionic compounds, and they trade partners. The cation over here will grab hold of the anion over here, and you'll get sodium nitrate. And then this guy's cation, silver, will grab hold of this anion chloride, and you'll get silver chloride. So in a double replacement reaction, you have two couples, two ionic compounds, and they simply trade partners to make the products. So two compounds, that's the distinctive way to recognize double replacement reactions. The last type of reaction is called a hydrocarbon combustion reaction. Now technically, a hydrocarbon is a molecule made of just carbon and hydrogen. So technically, just carbon and hydrogen. However, the hydrocarbon combustion reaction, sometimes we'll have compounds with oxygen also. So carbon and hydrogen, or carbon-hydrogen with oxygen. For this purpose, we'll consider those all to be hydrocarbons. And combustion means burning. To burn something, you have to chemically react it with oxygen. So in this case, we have a compound called ethanol, an alcohol. It's got carbons, hydrogens, and oxygens, and we're burning it. We're adding oxygen to it, okay, or oxidizing it. And as a result, you get two products that are the same in every one of these reactions. Whatever the formula of this compound was, if you have a compound that's a hydrocarbon or a hydrocarbon with oxygen, and you burn it by adding oxygen, you will always get carbon dioxide and water as your two products. Okay? There's no thinking involved in that other than to recognize, hey, this is a hydrocarbon and it's being burned by adding oxygen, then automatically the products are CO2 and water. Okay? Now in all these examples, you may have noticed that there were small things in brackets written beside them. Those are the phases of the reactants and products. The phases, the solid, liquid, gas, etc. So if you see S, that was a solid substance. If you see L, that was a liquid substance. G is a gaseous or gas substance. And if you see AQ, AQ stands for aqueous. And aqueous means it was dissolved in water. Okay, so back in our double replacement example, you didn't have solid sodium chloride and solid silver nitrate. You had a solution, aqueous, of sodium chloride being mixed with another solution, aqueous, of silver nitrate. In this reaction, solid silver chloride was forming and aqueous or dissolved sodium nitrate. Since there was a solid forming, you'd expect to see a precipitate in that reaction. Okay? So for now, we're just going to focus on classifying. We won't worry about your ability to predict phases, but those are the 5 basic reaction types. Now, in the real world of chemistry, chemical reactions, most reactions out there are actually none of those. Most reactions are just strange, different types of reactions, and so we're going to call those other reactions. They don't fit any of those types. But in grade 11 chemistry, we're going to simplify things by focusing of all the chemical reactions in the real world. We're going to mostly look at these 5 basic types in our first year of chemistry. So here is a worksheet we have in our grade 11 course, classifying reactions and balancing the equations. Let's just jump in and try to classify some of these reactions. I'm assuming from an earlier course you're able to balance them. Let's just try classifying. So question 1, I look here and I see 2 reactants, hydrogen, oxygen, and they're creating one product. Okay, if you think back to what we said a minute ago, if you have more than one reactant and you're creating only one product, then this is a synthesis reaction. So I'm going to call this S for synthesis. Now another name for this, because it's a synthesis, you could also call it composition, or in this case, because the reactants are elements combining to make a product, you could call it a simple composition reaction. Some teachers will use that term. I'm going to just call it a synthesis reaction. In question number 2, you look at the reactants here and you have an element, and it's reacting with a compound, and in this compound I see positive hydrogens and negative phosphate. That's actually an acid, but we can think of it as being made of cations and anions. So this kind of looks, if you recall, like that dancing situation. These two guys are dancing, the positive hydrogen and the negative phosphate, and zinc is wanting to come in and dance with somebody. So this is an element with an ionic compound. That was the single replacement reaction. Single replacement. The zinc, when it does become an ion, will have a charge of 2 positive, which means it will be attracted to phosphate. 2 positive zinc and 3 negative phosphate will give us a formula Zn3PO42. The hydrogen will come out as a new element, and because hydrogen is one of the diatomic Hofbrinkel elements, the elements that are made of 2 atoms each, we'll have a formula of H2. The third reaction has a compound, and it's forming 2 simpler things, 2 elements. So we have a single reactant and multiple products. That's the opposite of what we had in the first situation. So when you have a single reactant and more than one product, that's a decomposition reaction. In this case, because the products are elements, you could also call it a simple decomposition reaction. Number 4, this is sort of like the second one, looking at it. We have a compound with a positive and a negative ion, and it's reacting with an element. So this is like that dancing analogy. A couple here is dancing, and an element wants to come in and dance as well. So this would be the single replacement reaction. Now when chlorine becomes an ion, its charge is -1. So it's going to come in here and it's going to be attracted to the positive potassium. So the product will be potassium chloride, KCl, and then bromide, which used to dance with potassium, comes out as an element, and because it's one of those diatomic Hofbrinkel elements, its formula is Br2. Number 5, I see a compound here, but I recognize, hey, that's one of those special compounds. This is a hydrocarbon. It's made of just carbon and hydrogen, and we're reacting it with oxygen, that's like a combustion, that's burning. And the products, CO2 and water, well, that's enough. I know this is a hydrocarbon combustion reaction. The products are always CO2 and water. So hydrocarbon combustion. You're burning, in this case, that's called propane. So if you have a barbecue at home, a gas grill in your backyard, you probably have a tank of propane, and when you turn on the gas and light it in your barbecue, you're burning the propane gas, and you're creating carbon dioxide and water. Number 6, I see there 2 reactants and 2 products. And when I look at those 2 reactants, I notice that this guy is a 2 positive and a negative, and this guy is a positive and a negative. Recognize those as ions. So this is that situation, that dancing scenario, where we have a couple dancing and a couple dancing, and they're trading partners. The positive calcium grabs hold of the negative fluoride to give me calcium fluoride, and then the positive hydrogen, the negative hydroxide, gives me HOH, which we normally write as just H2O. But keep in mind that water technically is built like that, HOH. So it's often good to think of water as HOH rather than H2O. But this is how it's normally written, as H2O. So this is the compound, the ionic compound, in this case with an acid, which is made of ions, and they trade partners. So that's the double replacement reaction. Okay, now we've seen there quite a few examples. I think we've covered almost all of the reaction types. I'm going to have you take a look. If you'd like to pause the video and try the remainder of these questions, you can hopefully see them. Pause the video, try to classify them yourselves, and then when you're ready, press play again, and you'll see me with the answers here, and I'll do it pretty quickly. So number 7, a single reactant breaks into more than one product. That's the sign of a decomposition reaction. Number 8, I have an element by itself, and it's looking over here at a compound made of 2 ions, H and Br. They're dancing together, and this element comes in to dance as well. That's the single replacement reaction. Here we have 2 elements. This 8 doesn't really matter. Sulfur is a complicated element like the Hofbrinkel elements, but instead of being diatomic, it has 8 atoms. But it's just an element. So an element and an element making a compound, that's a synthesis reaction. CH4 was a hydrocarbon, carbon and hydrogen. We're burning it by adding oxygen, and it's producing, as always, CO2 and water. So this is the hydrocarbon combustion reaction. Number 11, I see 2 compounds here, and they're both made of ions. So the lead I know is 2 positive, and the nitrate is negative. This guy's positive, and this guy's negative, and they're just trading partners. So you're going to get lead chloride and potassium nitrate as your 2 products. When 2 couples like that trade partners, it's the double replacement reaction. Number 12, the thing that jumps out at me right away is that there's 3 reactants and 2 products. If you think about it, none of our reaction types fall into that basic category. If there were 3 reactants and only 1 product, then we could call that a synthesis reaction. If there was 1 reactant and 2 products, we could call that a decomposition reaction. But none of the other reaction types had 3 reactants and 2 products. So therefore, this is going to be an other reaction. Number 13, there's that strange sulfur again, but it's just an element reacting with another element to create a compound, so that is a synthesis reaction. Number 14, you have an ionic compound, 3 positive and negative iron and chloride, reacting with another ionic compound, positive and negative hydroxide, and they're just trading partners. You're getting iron hydroxide, and you're getting sodium chloride. When 2 couples like that trade partners, it's a double replacement reaction. The next case, you have an ionic compound, positive, negative, reacting with just an element. So you have a couple dancing and an element by itself. The element's going to come in and dance. The element is chromium, and chromium is a metal, and I know it's going to become probably 3 positive, looking at a periodic table. So it's going to come in and dance with nitrate. So chromium nitrate will be the product, and the silver will come out as just silver metal. So that's the single replacement reaction. Here we have a single reactant and more than one product, so this thing is decomposing into smaller things. So that's a decomposition reaction. Because the products are elements, you could also call it a simple decomposition reaction. Potassium chromate is an ionic compound, and nickel chloride, nickel 3 chloride, is also an ionic compound. So these are the ions dancing together, and they trade partners, and so this is a double replacement reaction. And the last type, 2 reactants. Now at first you might think that's looking like it could be a double replacement reaction because it's positive negative and positive negative. This could be a double replacement reaction, but there's 3 products. If it were a double replacement, they would just trade partners and we'd have 2 products. Over here with 3 products, that doesn't fit any of the reaction types that we saw, so therefore that's going to be an other reaction type. Alright, so classifying reactions, not that difficult once you've memorized the different types. Now sometimes a little bit harder is classifying and then using your classification to complete chemical reactions. So let's try a few of these. So in this first case, I see an element reacting with another element. So 2 elements reacting is likely going to be a synthesis reaction. And synthesis means those elements are combining into a single product. So in this case, calcium chloride is going to be the product. And using my rules for nomenclature that we learned earlier, I know that calcium is 2 positive when it's part of a compound, and chloride will be negative, so CaCl2 will be the formula of the compound. In the next case, I see an element reacting with a compound, and this compound has a positive and a negative, so this is that single replacement situation. The element is looking at these 2 dancing, and he wants in there to dance. So that's a single replacement reaction. Now you look on a periodic table and you notice that when zinc reacts, it will have a charge of 2 positive. Now as 2 positive, it will be attracted to the chloride over here, which is negative. So zinc 2 positive and chloride negative, the formula of zinc chloride would be ZnCl2. And then hydrogen is going to come out as an element, but it's a Hofbrinkel element, so plus H2 would be the formula of the other product. Now this reaction is not balanced. You had only 1 H there and you've got 2 here. So to balance it, we'll put a 2 here. And notice that that 2 gives me 2 H's, but it also gives me 2 chlorines, which I needed because there's 2 chlorines here, and we had 1 zinc, so we have a balanced equation. Number 3, a single reactant. If you have a single reactant, then it must be decomposing. It's breaking into smaller, simpler things. It's only made of 2 elements, so it's likely going to simply decompose into the element zinc and the element oxygen. But oxygen is a Hofbrinkel element, so O2 would be its formula. But we have 2 O's here, so to balance that, we'll put a coefficient of 2 here. That gives me 2 zincs, so I'll need a coefficient of 2 there as well. And now we have a balanced equation. Number 4, here is a hydrocarbon, and we're adding oxygen, so we're burning it. That's the hydrocarbon combustion reaction. Hydrocarbon combustion always produces carbon dioxide and water. There are 5 carbons here and only 1 in the carbon dioxide, so I can make that equal by putting a 5 there. There were 12 hydrogens here and only 2 in the water. I can balance that by putting a 6 in front of the water, and now I've got 12 hydrogens there. I've got 5 times 2 is 10, plus 6. I've got 16 oxygens on the right, but I only have 2 here on the left. So I can make that equal with an 8 in front of the oxygen, 8 times 2 is 16. So there's my balanced hydrocarbon combustion reaction. In number 5, I see one of the products is iron chloride and the other product is hydrogen. Thinking about that for a minute and the different types of reactions, that looks like it would be the product of a single replacement reaction where an element comes out by itself and a new couple has formed. Looking at that new couple, the iron is 3 positive and the chloride is negative. The hydrogen over here was dancing with one of these two, but hydrogen has a charge of positive 1 when it's an ion. So therefore, it would have been dancing with the negative chloride. So a positive hydrogen and a negative chloride means the formula was HCl, and that means the element that used to be by itself was iron, Fe. Okay, that makes sense. The Fe goes in and dances with chloride, iron chloride, and hydrogen comes out by itself. Now to balance that, we've got got to be a bit careful here. I'm going to do this very quickly. A 3 here and a 2 here is complicating things. I'm going to put a 6 in front of the HCl's. 6 chlorides, I'll put a 2 in front of the iron chloride. 2 times 3 is 6. 6 H's, I'll put a 3 in front of the H2. 3 times 2 is 6. And because there's this 2 in front of iron, I'll put a 2 here. So 2, 6, 2, 3 would balance that equation. We'll do one more, number 6. The products here are barium sulfate and water. Now you might want to remember water is better thought of as HOH, okay? A hydroxide and a hydrogen. It's a good way to think about water. So then in these two products we have a 2 positive and a 2 negative, and over here we have a positive and a negative, hydrogen and hydroxide. That looks like the product of a double replacement reaction where 2 new couples have formed. So what would the original couples have been? Well, the barium positive would have been dancing with the hydroxide negative. 2 positive and negative means its formula was BaOH2. And then the hydrogens positive were dancing with the negative sulfates. But sulfate was 2 negative, so plus H2SO4, that was sulfuric acid. To balance this, we have 2 H's and 2 OH's, so we're going to get 2 waters, 1 barium and 1 sulfate, and we're good. Alright, so there's classifying reactions in order to help predict the products, and then writing the formulas of the products using our rules for chemical nomenclature, and then balancing the equations as well. You can see things are getting more complicated. Perhaps the most complicated thing to do is to actually take a word equation and translate that into balanced chemical equations. And we don't have to, in some of these we may also have to classify the reactions to help predict products. Now in this first example, solid zinc metal is added to aqueous lead-2 nitrate. It yields, it produces aqueous zinc nitrate and solid lead metal. Okay, so this question tells me all the reactants and all the products. I don't have to predict anything. So zinc metal, Zn, now it tells me it was solid, so if you like you can put an S beside it. It was added to aqueous lead-2 nitrate. So I've got to use my rules for nomenclature. Lead is 2 positive and nitrate is a complex ion whose charge is negative. So this is going to be plus PbNO3 2, lead-2 nitrate. And then they're looking to me like a double replacement reaction, a single replacement reaction, but I don't even need to think about that because the products are given to me. So this is going to create zinc nitrate. Zinc is 2 positive again, so ZnNO3 2, and just lead metal, so plus Pb. And again, the phases, it told me this was aqueous, it told me this was aqueous, and the lead is just solid lead. Alright, so you can see in this, when you have a word equation, writing the formulas out, it requires that you remember all of your rules for nomenclature, and then you still have to balance the equation. By pure coincidence, this equation is already balanced, so we don't need to do anything. Looking at it, it appears to be a single replacement reaction. We weren't asked for that, but it could have asked us also to classify the equations. So there you have it, classifying equations, balancing equations, predicting reactants and products, translating word equations into balanced chemical equations.